if we have the complex equations and when we draw their graphs, then how we decide to move in this decided path or in this direction, sir? In what way we select the way or direction?
I mean, it depends. For example, if you are a physicist, okay, and you are interested in knowing that, okay, for example, what does Einstein said is that if the space-time is like a fabric actually. Okay, so you have this space-time fabric, and if something massive you are putting into the space-time fabric is going to bend the space-time fabric actually, and the lighter things, when they come into that curved path, they will start moving around, that curved path. But interestingly, you will see that, the small objects that are moving around the heavy object on that fabric are moving on a special kind of lines called the geodesics actually. Geodesics. So the geodesics are what, very roughly you can say that geodesics are the curves, which kind of gives you the shortest path between 2 points on the space actually. For example, if you are in plane, geodesics is the straight line. So what would be the shortest path to go from one point to another point on? So it's going to be line actually. So if you are on a sphere, the geodesics is these great circles actually. So in other words, if you are sitting on a plane and you want to go from say Islamabad, maybe somewhere outside or maybe Karachi, you will prefer to move on the great circles because the great circles are the geodesics. Sometimes we are interested in that, okay, in this space-time, if I am moving, along a certain direction actually, or on certain curve, what would be the, so when you are moving along, for example, geodesics, you can ask a question, what would be the velocity of the particle? So you need to differentiate the things actually. So if you want to differentiate, so particle is moving on object is moving on geodesics, so on a curve, and you are interested in computing its velocities, what do you need to do? So you have to differentiate on that curve actually, on that curve, okay, in the direction of the geodesics actually. So sometimes we are interested in computing the derivatives but in certain directions. Okay. An interesting point. Directional derivative, if exists, is an independent entity from the Fréchet derivative. Okay? If the function is smooth, like this, looks like this, then Fréchet derivative can also give you directional derivative. But it is possible that you are sitting on a point and you are not able to compute the change in all directions actually. So you are not able to compute the Fréchet derivative, the total derivative. But on that point, if you choose a certain direction, you are able to compute the derivative actually. So it is possible that Fréchet derivative doesn't exist, but the directional derivative exists actually. Okay? So the directional derivative is an independent entity actually. So you set up a basically vectorial direction and you are interested in computing the change. ठीक है? समझ आ रहा है? हल्की आंच पे? आंच तेज तो नहीं? यूं गुजर रहा है? 8 बज गए हैं? चलें. Okay. So now I would like to prove a property. Okay. I would like to prove a property, two properties, and then we will see that. It's so easy to compute all these derivatives. You can calculate it like very quickly. Okay. So here's a proposition. So the proposition says, so as I said, directional derivative may exist and Fréchet derivative may not exist. Okay? But if a function is differentiable, at a point, in other words, you are able to compute the Fréchet derivative, then there is no need to compute the directional derivative actually, because you do what? Take your Fréchet derivative and substitute the vector that you want to compute the change in the direction. You can really easily compute the directional derivative. You don't need to do anything. So here's the proposition. So the proposition says this. So if f is differentiable at a point A, okay, then all directional derivatives of f at A exist. That's a very good news. So the function is differentiable, smooth at a point A, okay? Then you can find all directional derivatives. Question how? Answer very easy. So you do what? So if you want to compute, okay, and so if you want to compute the directional derivative of f at A in the direction of a given vector x, then do one thing. Since the function is differentiable, this means that you have Fréchet derivative. Okay? You have Fréchet derivative. So take your Fréchet derivative and substitute x onto it. And you get the directional derivative. Okay? So in other words, and that's an important point here, from the directional derivatives, this is also possible. At a point, you can find the derivative in all directions, but the total derivative doesn't exist. ये भी हो सकता है. Directional derivative exists in all directions, but the total derivative doesn't exist. But once total derivative exists, then you can find the directional. This is a directional derivative become a particular case of it. You don't have to do anything for doing it. So what would be the quick proof of it?
सर अगर हम आर डार्जेंस डेरिवेटिव ले सकते हैं तो वो टोटल डेरिवेटिव हो सकता है.
This is good. That's a key point. Total derivative is so here's the thing. Total derivative is a thing that can give you the change at a point on a given function at once actually in all directions. At once, kaboom. Like you have roughly. So like I gave that mask example, So it just fires in all directions at once. Okay. But if the directional derivative exists, okay, this means that you can choose any direction and compute change in any direction, but it doesn't mean that you can compute the change in all directions at once actually in a single instant. So there's a difference between both. When you are doing directional derivative, you are fixing an instant and a direction and computing the derivative. Okay. So it's like asking the question. So I have one gun that can fire the bullets in all directions at once, and I have one gun, like an ordinary gun, which can at the moment just fire the bullet in just one direction actually. So there is a huge difference between both. Okay, so that other what do you call a robot type gun or mask type gun can give you the can fire the bullets in all directions actually. So that's what is the key thing. Anyway, roughly. So this is what I would like to show. So if a function is good at a point f,
ये जो बात करें तो फ्रेशेट डेरिवेटिव की, ये मतलब फंक्शन के हर कंपोनेंट का डेरिवेटिव होता है. फ्रेशेट डेरिवेटिव फंक्शन होता है, उसके सारे कंपोनेंट्स जो होते हैं वो भी सर स्केलर वेरिएबल फंक्शन होते हैं.
Yes.
तो सर जो फ्रेशेट डेरिवेटिव निकालेंगे उसका तो वो हर कंपोनेंट का होता है.
Fréchet derivative, you can even compute the Fréchet derivative for a scalar-valued function as well.
सर अगर वेक्टर वैल्यू फंक्शन का फ्रेशेट डेरिवेटिव
So you just compute the.
तो सर अगर उस कंपोनेंट्स के अंदर कोई ऐसा कंपोनेंट है जिसका फ्रेश डेरिवेटिव ना हो
This is very good question. This is very good question. This means that you can't. In other words, you have tried to find a direction, in which you can't find the derivative. This means that fresh derivative doesn't exist. So you can also have that. So the existence of the directional derivative is necessary for fresh derivative. But the existence of the fresh derivative is sufficient for the directional derivative. So if you can find one direction in which you can't compute, for example, fresh derivative, that means you can't compute directional derivative, that means you can't compute the fresh derivative at that point. Okay? Simple as that. Okay? These are good questions. So what does this is telling that if the fresh derivative exists, then the directional derivative exists actually at that point in all directions. This is what is the key thing. So define a path. So how can I prove it? Let's convince ourselves why this should be true. Define a path. E, okay, from I to Rn, okay, by P of t, which starts from A and give you A plus dx actually. So it's a line act. Okay, which is geometrically a line through A in the direction of x. Thus, what would be P of 0? What would be P of 0? So it would be A. And what would be P prime of 0? So it would be vector x. Okay. And since f is differentiable at x, okay, so since f is differentiable at a, so it follows. So this follows that if I compute the directional derivative of f at a in the direction of the x, okay, then this is same as what? This is same as limit t goes to 0, okay, what? A plus tx minus f of a over t. By the way, if you see, you can also see j.
So t prime of 0, so x k is also equal. So t prime of 0, so equal to 0.
T prime of 0. So differentiate with respect to t. So this will go away. Plus this will become 1 and you get x. Okay. So this is the definition. By the way, can I write this as, I mean if you see, would you agree with me that this is same as that you compose f with the p and compute the time derivative and evaluate it at 0? Step is going to be, so I know from my previous proposition, path property, that this is equal to what? The Fréchet derivative of a evaluated at p prime of 0. Okay? But p prime of 0 is what? That's it.
Why we make the use of tangent vector in this directional derivative?
What do you mean by that?
So we are using that tangent vector in this directional derivative.
In other words, line is a kind of a vector. So what is the tangent vector on the line? What would be the direction of the tangent vector on the line? So that's what this thing is telling you, that if you compute the tangent vector on the line, because this is line, you always have the direction of the x. Okay? So you have it. Anyway. So what does this theorem is telling you? Telling you that we know how to compute Fréchet derivative. So if I know that function is differentiable at a point A, then there is no need to compute the directional derivative from its definition. Just take the Fréchet derivative and substitute the direction x, and that is going to give you the directional derivative actually. ठीक है जी?
सर थोड़ा प्रूफ को समराइज कर लें.
Proof summarize कर दें. So he said, imagine you have a path A. Okay, so that's I'm giving just this guy a name actually, P plus P of t. Okay, so path is what? So define a path P, okay, from the suitable domain into Rn as a line that passes through A and goes in the direction, goes forever in the direction of the x-axis. Okay, and then if I substitute 0 in it, I'm going to get A. Okay, and if I differentiate it with respect to time and substitute 0 in it, I'm going to get the vector x. Okay, so this vector x on the path becomes the tangent vector on the line actually. Okay, and then I'm saying that okay, take the definition of the Fréchet derivative. ठीक है? So the definition में भी देखें ना. Okay. Alright. I mean if you okay, take the definition of the Fréchet derivative. ठीक है? By the way, क्या मैं इसको यूँ लिख सकता हूँ? Okay. So this limit. If you are not happy with this actually, so I would like to rewrite this in another manner. So what you need to do? This means that take your f of a plus dx, okay, differentiate it with respect to t and substitute t equal to 0. So is there a difference between this line and this line? Okay. So if you are computing, if you are computing the, what do you call this limit with respect to the parameter t actually, so what you are essentially saying is that, okay, let's compute the derivative of the t, okay, and then substitute t equal to 0. And what is this guy? So a plus tx is p of t, so this is f of p of t, so you are differentiating it with respect to time, so this would be f composition p prime of t, and then you are substituting t equal to 0, so you get f composition p prime of the 0. And from the path property, we know this guy is equal to this, okay, and the p of 0 is x, so you have it. Okay, one last thing, and then maybe I'll do last remarks actually. So I would like to make a remark. If I want to compute the Fréchet derivative, the directional derivative of f at a, but not in the direction of x, but in the direction of a scaled x actually, where lambda is a number. So maybe half f x or 2/3 x or 2x. Okay. So lambda is a number. So lambda is a real number. So if you want to compute the Fréchet derivative, directional derivative of the function at a, but in the direction of a scaled x, then the interesting thing that we can prove would be what? It would be that it's lambda times of the directional derivative of f in the direction of x. Okay? You may verify it from the definition actually. Okay? It's very easy if the Fréchet derivative exists because d lambda x of f of a is equal to the d f of a of lambda x actually. And I know that the Fréchet derivative is a linear transformation, so you can pull out that number actually. Correct? So that would be the case when function is differentiable. Okay, the interesting thing would be that can I verify it from the definition actually? I think it shouldn't be a difficult thing, so give it a go. That what would be, ये जरूर prove कीजिएगा, try to prove it. Second thing that is interesting. So if I have a dx, the directional derivative in the direction of f in the directional derivative of f in the direction of x evaluated at a, okay, then I know that every vector can be written as what? A unit vector multiplied by the magnitude of x. So this x is same as this actually, times of f of a. Okay, and this is same as that you compute the magnitude of x and compute the derivative of f, but in the direction of the unit vector actually. This identity holds also from the top equation actually. Okay, so in other words, if you want to, so in other words, if you have the directional derivative in the direction of what do you call unit vectors, then you can find the directional derivative of any vector that is, you know, parallel to this vector actually, very easily by just multiplying with the magnitude. Okay? So let's try to write a consequence of this thing, this observation. Okay? Let's try to write a consequence of this observation. Let's take x. So x can be any direction. So I can, if I wish, I can choose x to be, you know, E1. So 1, 0, 0, 0, 0, 0. So even if I wish, I can choose it to be E2. In other words, I can choose x to be EJ. So I would like to, you know, see the directional derivative of the f, the given f, but in the direction of these basis vectors, the basis unit vector. And these bases are the what? These are the bases of Rn. Okay? And the question is, see what we get. See what we get actually. You're going to get something very interesting. Okay. So see, things are connected with each other. They are really linked. Alright. So let's compute, okay, the directional derivative of f, okay, at a, but in the direction of E1. Okay, in the direction of E1. So what would be this by definition? What would be this by definition? So this would be limit, by definition, limit t goes to 0, a plus t E1 minus f of a and everything divided by t. ठीक हो गया? So if I write it explicitly, limit t goes to 0, so f of a plus t1 is going to be what? So this is, so a is like a1, a2 and an, and te1 is what? So this would be, so e1 is 1 0 0 0 0. So te1 is going to be t 0 0 0 0. So this would be a1 plus t, okay? 2 0 0 0. a3 and an minus f of a over 3x, where the t goes to 0. So do you recognize this guy? What is it?
It's the same total difference.
It's what? Have you seen something like this before?
Sir, 8.A1.
If you haven't seen it, let me show you. Have you? Huh? So it's a partial derivative. Okay? This is nothing actually. This is just partial derivative. So it's a partial derivative with respect to the first variable actually. So it's partial f by, partial x1, where x1 is, is the direction of the even up. So this is nothing. This is just. Yeah. So what is the definition that might have learned by what is partial f by partial x? So if f is a function of x and y, how do we define partial f by partial x? So you say that limit delta x goes to 0, f of t plus delta x y minus f of x y over delta x. Have you seen something like this before? So that's the definition of the partial derivative. You haven't seen it? Now see it. If you haven't seen it, now see it. Okay? So what is happening actually? So the partial derivative is just giving you the change in the direction of x actually, okay? So what does it mean? So you will put an increment in, no, it shouldn't be t, it should be x actually. Because x plus delta x, y, and minus. So that's if xy is a point here, okay, so where would be the x plus delta x? So it would be really the point right in front of it actually, adjacent to it, so x plus delta x y. Okay, so evaluating it and then dividing it by 0, so that's what the definition of partial f by partial x is. Similarly, you can have partial f by partial x. So if I have, instead of x, I have a 3 variable here.